All right, hello everyone. Today we're going to be solving LeetCode 1971. Find if a path exists in a graph. First, we'll start off by reading the problem statement. There's a bidirectional graph with n vertices where each vertex is labeled 0 to n minus 1 inclusive. The edges in the graph represent 2D integer array edges where each edges I, is an array with two integers u and v, which denotes a bidirectional graph between vertex u and vertex v. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. You want to determine is there a valid path that exists between the source and destination vertex. Given edges and integer n source and destination, return true if there's a valid path from source to destination, otherwise return false. So as you can see, this is an easy, and obviously it's a graph problem. So this is very good for beginners in graphs, and that's why we started off with it. Let's quickly go over why these are the answers. We see we're given this edge list, and we see the source is 0 and the destination is 2. So from this picture, we can clearly see that 0 can reach 2. Just go over this this edge. In the second example here, we start off with a source of 0 and a destination of 5. 0, there's no way you can bridge the gap between this graph and the second graph, therefore we return false. All right, so I'm going to show you guys how we would go about solving this. Whenever you receive an edge list, let's say there's a 90% chance you're going to have to make an adjacency list. An adjacency list just is essentially a dictionary in Python where the key will be the name of the edge, i.e. like since it's 0 to n minus 1, it'll be a number, and the value will be a list of all edges it connects to. So in this example here, we'd have a dictionary with the keys 0, 1, 2, and we see that, hey, 0 connects to 1. So that means that in this array, there should be a 1. Quickly write that. Oops. A 1. So we've checked this off. But there's actually something interesting. It says that there's a bidirectional graph. So that means that there is an edge between 0 to 1 and 1 to 0. So we have to go to the 1 as well and put the 0, because it's like a road that has two ways through it. You know, if there's a one-way road where you'll go, it's like you call that a directed graph. But if it's unidirectional or bidirectional, there's an edge in between both nodes. So that's why we have to add a connection on both of the keys. And we do the same thing here. So from 1, there's a connection to 2. And if there's a 1 connection to 2, that means that 2 connects to 1. So we go to 2 and we add a 1. And lastly, it says 2 connects to 0. So 2 connects to 0, but that also means that 0 connects to 2. Right? All right. So what we're going to do now is have a depth first search algorithm that's going to start from the source node, and we see that our source is 0. So here, let me quickly highlight that in green. We're going to start at our source node, and we're going to traverse the graph either until we run out of nodes or we find the destination node. And if we run out of nodes, we return false, and we find destination node, we return true. And you might say, hey, how do we know if we've used up all the nodes? Good question. What we're going to do is use a set, and it's going to be called seen or visited. Let's just call it seen for now. Excuse my bad handwriting. Seen. Okay, so we have a seen set, and every time we traverse a node, we're going to add it to seen because we don't want to traverse a node multiple times. Like, let's say we went from 0 to 1. We don't want to go from 1 back to 0. That would be redundant. So we start off at our source node of 0, and first we go to 1, right? We go to 1, we add that to our scene, and remember 0 is in our scene because we started there. So 0, 1 is now in the scene, and now we're at node 1. So now we're at node 1 here, and we say, hey, node 1 could either go to 0 or 2. We check 0, and we say we've already been there because we're at node 1. We don't want to go back to 0. And the next option is, hey, we can go to 2. And we check, is that in scene? It's not in scene, so we're going to traverse there and add it to scene. Now it's in scene, and we're currently at the 2 here. And what do you know? Ding, ding, ding. This node is equal to our destination node, so we can immediately stop and return true. We don't have to go anywhere else from 2. Not that we could go anywhere else, because as you can see, from 2, 1 and 0 are its neighbors, and both of those are in scene, so we can't use them, unfortunately. But that is pretty much the idea behind a question like this. So let's get into how to code it. Let's quickly zoom in for you guys so you guys can see. Hopefully that's good enough. So first I like to make the adjacency list. So we're going to say adj for adjacency equals default dict. And if you don't know how default dict works, it essentially is a dictionary in Python, but if you try to add a value that doesn't exist, it's going to default to something. I'm sorry if you guys hear the lawnmower outside. I can't really do much about that. But as you can see, the values inside of our dictionary are lists, which will store the integers of the neighboring nodes. So that's why we put the default dict to list. Next, we need our scene, which is going to be a set of all the nodes we've seen. So equals set. And here's the fun part. We're going to make our adjacency list. If you feel comfortable or you know a little bit about adjacency list, feel free to pause the video and try it out yourself based on the explanation from the Excali draw. But I'm going to quickly show you guys here. So I'm going to say for UV in edges. So this means that U connects to V and V connects to U. So what do you think we do? We go adjacency at U dot append V. So that means that edge V or node V has a connection to V, or node U has a connection to V, and we do the same exact thing for V. So node V now has a connection to U. It was the same thing we did here, just like when we saw that 0 connected to 1 and 1 connects to 0. So that's making that edgeless, and it should look exactly like this when we're done. So now that we have our edgeless, we want to create our depth first search function. So we're going to say define a function. So define DFS equals node. So we're going to start off with a node. And since depth first search, as you guys probably know, is a recursive function, we need to have a base case. So what's the base case? It says if node equals the destination. So if node equals destination, we want to return true, because that means we found the node. Next, what we want to do is iterate through the adjacency list. So we're starting off at node. So we're going to say for neighbor in adjacency at node. So this will, just like in the first example, when we start off at 0, it's going to iterate through all of its neighbors. And that's why I put na for neighbors. All right. So that's going to iterate through that. And we're going to say, first we want to check to make sure that it's not in scene, because we don't want to go back to a node we already explored, because that would be redundant. So if na not in scene, we want to add it to scene, because we don't want to go there again. And then we want to traverse that function, or traverse that node. Just like when we were in the first example here, we see that 1 wasn't in scene the first traversal. So we're going to go to 1, which is the depth first search call, and then we're going to explore 1, and we keep doing that until all nodes have been explored. All right. So next, what I like to do is actually return the call. So if we call depth first search on the neighbor node and it returns true, that means that the destination node was found. And if it returns anything that's not true, that means the node was not found, and we've traversed all the nodes because scene would have been filled, right? So we do if DFS at neighbor. So that means if DFS at neighbor is true, which means it returned true, so that means one of the nodes equal destination, we want to return true, right? And if it gets past this and it never equals true, all we have to do is just return false, because that means that we've traversed every single node, because the scene ensures that every node that is connected will be seen. And if we can't reach the destination node, because this cause on line 15 has never been enacted, that means that we can't find the node, so we return false, right? So here, lastly, all we have to do is pretty much add these things to our scene. So we're going to say scene dot add source. And we're adding source because when we start off the DFS call, we always start from the starting node. And let's say we started off at node 0, we would add its neighbor first. So 0 would never actually be inside the adjacency list, and it would actually bring us back. Like, let's quickly look at this example. If we didn't add 0 beforehand, we would start off at 0, and we would go to 1, right? And 1 would be added. And then we go to 1, and we see that we can go back to 0. That's doesn't make any sense. We don't have to go back to 0, but the scene doesn't know we've been there. So that just ensures we don't go back and do any extra work. And next, all we have to do is return you DFS at source, because we always want to start off at the source node. And this should be the answer. Let's try it out. Oh, a quick typo. Default dict. Added an A there for some reason. There we go, and we solved the problem. So it's relatively efficient, and you just solved your graph problem. Just make sure do not have any typos like me.